welcome everyone to the March 2022 edition of IndiePie. We have a great guest this evening. Super excited to get started with that. So I'll rip through these announcements, but there are some super important things on this month's announcements. So if you're just going to not pay attention because it's always the same thing I always used to say, not this time, watch out. We're going to kick it off right away with Happy International Women's Day. I'm super excited that we are having this on International Women's Day. So if you've got an international woman in your life or just a woman in general, you may want to go say how much you appreciate them and celebrate their day. All right. Now, moving right along, this is some of the biggest news of the day. Well, part of the biggest news is that IndiePie is going to be celebrating 15 years. So it's our 15-year anniversary. And we're going to do it in person. So May 10th at the District Tap on the north side. So some of you may be familiar. We've done a couple events there pre-pandemic. So we will be getting together in person for our 15-year anniversary. Make sure you RSVP at meetingplace.io. There will be fabulous prizes, certainly a cake. And I'm sure Pete the Python, if you've ever met Pete the Python at our meetups, will make a guest appearance and you can get your picture with him. So it should be tons of fun. Do we have a speaker lined up, Laura, for that? Not yet. So look forward to more information on that. But I think the important bit is we're going to be getting together in person to hang out with all the other Pythonistas from Indy. And I think Ari, one of our sponsors, is going to fly in and hang out with us. Actually, is Ari here? I can't see all the people.
Not yet. Not today.
Not today. Oh, okay. That's fine. But yeah, we should see some great faces all hanging out for our 15-year anniversary. I'm super excited about this community. I love building what we've built here in Indy, and I'm really proud of the Python community here in Indianapolis. Speaking of all that, let's make sure you follow IndiePie on Twitter. If you are live tweeting tonight's event on the Twitter sphere, make sure you use the IndiePie hashtag. We should be seeing live tweets coming from the IndiePie account. So if you wanted to comment or follow or add questions or context, please feel free to do that tonight on the IndiePie Twitter account. I want to thank our sponsors. IndiePie couldn't be possible without our awesome sponsors. So our organizing sponsor is 6 Feet Up. IndiePie is brought to you by 6 Feet Up. And 6 Feet Up is a Python and cloud consulting company that helps innovative tech leaders build apps faster, innovate with AI and ML, simplify big data, and leverage cloud technology. Using modern technologies and processes, we make anything possible for our clients. I'm Calvin Hendricks Parker, and I co-founded 6 Feet Up in 1999 and have been the CTO ever since then. And super excited to be participating in this community. Also want to thank our platinum sponsor, JetBrains. So look forward to a couple PyCharm professional licenses at the end after our speaker tonight. Our bronze sponsors. So actually Jeff's here from Reify Health. So Jeff, if you want to give a quick little spiel, I'm happy to give you the stage for a moment.
Thank you, Calvin. Thanks, Calvin. Thanks, Laura. Happy International Women's Day to all the international and domestic women in your life. Ooh, that probably didn't sound good, the domestic women. That was a pun that kind of fell flat. So congratulations on 15 years, Calvin. That's a spectacular milestone. That's been great work. So proof of the staying power of the Indianapolis tech community for sure. So congrats again. My name is Jeff Stickle. I'm Director of Engineering for Reify Health. We are a cloud-based clinical trials SaaS company. We make products and our applications to shorten the clinical trial life cycle and improve their chances of success. And then hopefully through that, bringing meaningful life-changing outcomes to humanity and people in general. We are very mission-centric. We are very driven, and we are growing very quickly. In 2020, when I joined, we had 25 engineers. We finished that year with 40. We set an aggressive goal last year to double that, to hit 80 by the end of 2021. We actually hit 100 engineers in July, so we kind of crushed that goal.
Wow. Nice.
Now we're on to about 160 engineers, probably be about 260 by the end of this year. So we're growing like crazy. We need engineers of all ilk, developers, testers, Python, Clojure, JavaScript, you name it. We are a scale up for sure, not a startup. Our software has been using at clinical trial sites somewhere around 70 countries worldwide right now. And I think we've spun up over 1,000 clinical trial sites. And I believe we have over half of the top 20 pharma companies as our customers. What's my tie to IndiePie? Well, I've lived in the Indianapolis community for about 30 years here and been working in it ever since. And was super happy to get introduced to Calvin and Laura, and they were gracious enough to give Reify Health a chance to be a Brown sponsor and participate in your meetups. So
will you join us on the 15th anniversary in person?
I would love to. I love the district tap. It sounds spectacular. Right? Forgive me, I've already lost it. Is the one downtown or is it the one up in Nora?
The north side one.
Oh, great. I have a great story. I'll tell you when we get there sometime.
Perfect. I'll make sure I remind you of that one.
Yeah, please do. I'll drop a couple of links in the chat, in the Zoom chat for folks here, as well as my email address. Please don't hesitate to reach out if you have questions. I'm also active on Slack, easy to find it in the Indie Hackers community. Back to you, Calvin. Thank you.
Thank you, Jeff. We appreciate your sponsorship. Our other bronze sponsor is JFrog. We want to thank them for they've been sponsoring now for 2 years, and they have one of our door prizes tonight as well. So if you see an Adafruit clue coming your way, you can thank JFrog for that opportunity. If you want to become a sponsor, or if your company would like to sponsor IndiePie, if you're doing awesome stuff with Python and want to make sure you can help the local community grow, there is an opportunity for you to be a sponsor here. If you go to indiepie.org/become a sponsor, or just email laura@6pf.com, we will get you hooked up and give you the spotlight here at IndiePie. If you want to, we can also join our Slack. We have a jobs channel there. So if you're looking for a new career, or if your company is hiring, we really welcome you to post there in the jobs channel on the IndiePie Slack, and you can get the invite link there from the bit.ly link and join the Slack. It's a pretty low traffic, but I tell you what, if someone asks a question, you typically get some pretty darn good answers. So make sure you leverage that as an opportunity for you to grow your Python skills. Python skills indeed. We have got the 4th annual Python Web Conference coming up this month, March 21st through the 25th. Do not miss this one. We have got over 90 speakers participating in this conference. It has grown from a single day, 3-track event to a 5-day, 6-track with tutorials, amazing extravaganza. And I'm super excited for the diversity of the speakers we are bringing to the table. If you go to pythonwebconf.com and click on the speakers link, I would invite you to not be impressed by the speakers who are going to be joining us this month at Python WebConf. So it's really crazy just how many people are all excited about being on board. We're looking at 400 to 500 attendees. We'll have a Slack running so that people can participate and engage 24/7 during that week. All the videos will be up instantly. So once a talk is given live, they're available for you in about 10 minutes after that. So you can watch, if there was a conflicting talk that happened side by side with the one you didn't want to miss, never fear. You can actually watch it 10 minutes later and have that experience while everyone else is also enjoying Python Web Conference. So definitely check it out. If you look on Twitter, follow the Python Web Conference Twitter account, you probably find a discount code. From IndiePie is also probably got a discount code on our Twitter account. So if you look at the Twitter sphere, you'll find some discount codes. Make sure you tweet about it too using the hashtag PWC2022. I hope to see you all there. I'm really excited. This year's going to be bigger and better than ever. And just, again, love building community. Super excited to have everyone join us for a week of Python fun. There are going to be 2 app dev tracks, a cloud track, a PyData track, and a culture track, in addition to tutorials running every day of that week. And then beginning of day and end of day with a different keynote speaker in each of those slots every day. So tons of amazing, amazing content and talent coming to speak. So hopefully we'll see you all there. Speaking of, if you want to make IndiePie better and you want to win a ticket, this is the little hook I had for you all. There is a ticket giveaway tonight. We will be giving away a free pass to Python Web Conference tonight if you help us make IndiePie better by going and answering one simple question at this link. So it'll take you to a type form where we're going to basically ask you who you want to hear at IndiePie, what topics, what speakers, who can we bring to the table for you all to learn from and ask questions to during our event. So go to that. The drawing for those will be, Laura, how long are we giving people to fill out this survey?
You will have until Wednesday to fill out, and you will have until Monday this week to fill out the survey. So the winners will be announced on the 14th, Monday.
Okay, so you got a little time, but make sure you put some good thought
It's
into
literally
this.
one question. So just
One question.
And I'm about
It's
to
not
put
hard.
the link in the chat so you can all find it.
Okay, so I'll reiterate this again, like the last 2 years I've been reiterating it, is we have moved to meetingplace.io. If you've not moved your meetup.com profile over to meetingplace.io, please do. That is the only way for you to be in the running for the door prizes. And the door prizes tonight are off the hook. We have got not only the normal 2 PyCharm professional licenses available and the Adafruit Clue from JFrog, but you'll also be in the running for a free pass to Python Web Conference. So if you're interested in going to Python Web Conference this year and you haven't bought your ticket yet, hold on, wait until the end of this talk because I will do a drawing and we will give away 1 ticket to the event. So we will hopefully see you at the Python Web Conference as well. Okay, enough announcements. I know I kind of let that one stretch on a little longer, but it was important announcements tonight. We had lots of good stuff to talk about, and I hope to see you all at Python Web Conference, and I really hope to see you all at the 15-year anniversary. With that being said, I'm going to stop and actually turn this over to our guest speaker, Sanjay, who is going to be talking to us about workflow engines in Python. So I'll go ahead and stop my share. If you've got questions, feel free to drop them in the chat or on Twitter. Laura and I will be watching both those spots, or please feel free to turn your camera on, unmute, and ask questions in real time. So I'll turn it over to you, Sanjay.
Thank you all so much for having me today. I'm really excited to chat with you about who we are at AKASA and workflow engines and a lot of the technical challenges that we face. So I wanted to briefly introduce myself first. My name is Sanjay. I'm a Director of Engineering at AKASA, and I've worked in the intersection of healthcare and technology for my entire career. And I really love working on software to help people have a better experience with healthcare. We all use the American healthcare system, and I think many of us can attest that we've maybe had bad experiences with medical billing or other parts of it. And one of the goals I have out of my career is to hopefully play a small role in making that better for all of us. I joined AKASA as one of the first engineers in 2019 when we were a seed stage startup. And right now I'm managing a few teams that focus on our AI-driven automation platform, as well as our data engineering team. And before this, I studied at Stanford and I studied computer science and biomedical informatics. And relevant to the IndiePy group, I actually grew up in Carmel, Indiana, and lived there for about 10 years as a kid. And so it's good to be back virtually and be able to participate in the IndiePy community. So thank you for having me. So most people probably haven't heard of AKASA, given that we're a small startup. I wanted to take a couple minutes to chat about what we do before I jump into the technology. So healthcare spending in America is growing way too fast. And this is one of the biggest threats to financial stability for American families. So they actually say that the largest cause of personal bankruptcy in the US is due to unexpected medical bills. And on the bottom left here, I'm highlighting this stat, which is that 1/4 of all annual healthcare spending is considered wasteful. And of that category, over $250 billion every year are spent on administrative expenses within the healthcare system. And AKASA's goal is to help bring the cost of healthcare down and make healthcare more affordable for everybody. I want to highlight just a couple stats here without getting too much into healthcare jargon. First, I'll start on the bottom right side, which is that almost 80% of healthcare providers and hospitals are looking for automation for some portion of the revenue cycle, which is basically medical billing and health insurance within the next year. So especially because of the COVID-19 pandemic, healthcare providers have really seen the need to have automation that can do quote unquote auto scaling and scale up and down based on how many people are coming in to see the doctor, or how many people are in the hospital, and having automation that can better keep up with fluctuating workloads. And on the bottom left here, what we're tracking is a metric called cost to collect, which says, if I'm a hospital system, what percentage of my total revenue do I spend trying to collect money from health insurance companies? And the hope was that over the last decade, as technology improved, you would see cost to collect as a percentage of revenue come down. But what we see is it actually remains stagnant, meaning that we didn't really make a dent in it from 2011 to 2017. And there's a lot of opportunity there to continue improving this system and bring this percentage down to a much, much smaller number. And that's basically what AKASA's goal is. So what we want, RCM stands for Revenue Cycle Management. And what we want to do for the healthcare system is build robots that can automate all of the repetitive administrative tasks and allow people at hospital systems to focus on patient care. And if we do this, we think that patients will have a better experience with healthcare, and the cost of healthcare will be reduced significantly. I also wanted to mention that AKASA is growing extremely fast, which is a result of all the success we've been having and all the value we've been delivering to our customers. So in the past 2 years, we've gone from about 20 to 200 employees. And our customers collectively do about $100 billion in patient revenue each year, which is huge. And that's a huge opportunity in front of us to help them achieve cost savings and make healthcare more affordable. And our product is live in all 50 states, which still feels incredible to say. And over the past couple of years, as our data engineering challenges have picked up as well, we're starting to receive large ingests of data from all of our customers. And our machine learning models are now trained on over 200 million insurance claims. And I want to talk a little bit more about what a robot does, or what AKASA does, because I know I mentioned that term. So AKASA uses machine learning to automate tasks that can't be done via APIs, or where there are not APIs to support these tasks. So as an example, one of the tasks we have to do is do data entry in what's called the electronic health record, or EHR system, that the hospital uses. Just zooming in on this for a moment, the EHR system is basically the backbone of a hospital. It's a desktop application backed by a database, and it's the application where doctors' notes, lab tests, prescriptions, and all of those things are stored. And most EHR vendors do not support extensive APIs right now. And while there's a push to try to make that happen, even upcoming technologies like FHIR and HL7, which are healthcare-specific API protocols, are mostly focused on clinical data, but not much focus on billing data. And what that means is that in order to automate medical billing work for our customers, we have to build digital robots or Python processes that can actually log into the front end of the user interface of these applications and do data, like use computer vision, take over the keyboard and mouse, and do data entry, do scraping, do things like that. And we can do the same thing for websites as well. So we also build web scrapers, for example, for health insurance company websites, to automate common questions that the hospital has to ask the health insurance company. So broadly, one of the core parts of AKASA's technology is that we use machine learning to build an API for any manual task that uses the graphical user interface of a software system. And we've put a lot of effort into this, and that's going to be a lot of what I'm talking about today. Diving into this one level deeper, AKASA has a few different types of APIs, and I like to split them into two categories. One is called workflow automation, and another is called information extraction. These are sort of two different types of machine learning tasks. So when we're talking about workflow automation, what I'm talking about here is navigating through the front end of a system, scraping data, doing data entry, basically replicating a series of clicks and keyboard actions and things like that. So we may need to navigate to a specific claim in the electronic health record. We may need to take that info about the claim, take that from the electronic health record system, go open up a web browser and have our bot type that info into the health insurance company website and get a response back. And based on the response, we might need to go update the state of the claim in the electronic health record system. So this is what I call workflow automation, which means that instead of people having to do manual data entry tasks like these, we can do them instead. Second type of task is called information extraction. So for example, if you go to the doctor's office and every time you go, they might scan your insurance card. And that basically gives them a JPEG or a PNG with your insurance information, but that's not indexed and searchable in a way that allows them to do analytics on that or automatically tell if your insurance is still active. So what we can do is we can take these scanned images of insurance cards, and we've built custom machine learning algorithms to run optical character recognition on them and pull out all of the structured insurance information. And similarly, if we build a web scraper and we get a web page back from the health insurance company, we've built special purpose machine learning algorithms to extract the relevant data from that web page. So the reason I'm kind of setting this context is it's going to be relevant to why we ended up building a workflow engine and how we did that. But basically what you can see is that if we put these two types of APIs together, what we get is we can do workflow automation to navigate to the place in the EHR where the insurance cards live, download the JPEG for each insurance card, send it back to our servers, and then we can run our information extraction algorithms to pull out all of the structured data from the insurance card, and then go back into the EHR and enter that in a structured way that's now indexed and it's now searchable. So I just wanted to give that overview. And I think I see some activity in the chat. If there's any questions, let me know. And I'm not monitoring the chat, so feel free to just...
I'm watching it for you. I think we're good. There was just me responding to another attendee.
Okay, awesome. Other thing I wanted to say is that human support is critical for automation challenges. And AKASA's model, actually, we build our technology very similar to the model of a self-driving car. So high-level analogy there is that we're building computer vision algorithms to help our bots understand and automatically detect what they're seeing when they're in the front-end user interface of an electronic health record system or of a health insurance company website. So we're not doing any hard coding of, click here, then click there. Instead, we're using what we call a perception algorithm, which is machine learning algorithms that can tell our bot where to look. Similarly, and of course, that's how self-driving cars work, as well as they're building perception algorithms for things like lane detection and stoplight detection and things like that. Similarly, we don't manually monitor our bots. So we have telemetry set up so that our automations are constantly sending data back to the servers. Just like a self-driving car is instrumented with all sorts of sensors to collect different data points and send them back for analysis. And one thing that's in common with both the AKASA model and the self-driving car model is that you need human support in some cases. And so just like many of the self-driving car companies have this sort of call center where someone can remotely take over control of the car, we've implemented the same thing for our automations. So what we've built is all of the software and operational challenges so that if our bot ever has low confidence when it's going through something, it'll never do the wrong thing. Instead, it'll just pause and ask a human for help. And a human can actually jump in, take over the machine that the bot is working on. And as the human completes the task, the bot can watch and retrain itself based on that. And this is really important, but it also comes with some challenges, which is that right now we don't have a 24/7 human support. We have human support during certain extended business hours. And that means that if the bot hits a roadblock in the middle of the night, for example, there's going to be a lot of latency until it gets support from a human. And what we've been thinking of a lot is, how do we deal with this latency? And how do we make sure that our bots can still be productive when they're dealing with a combination of very quick synchronous tasks, but also some high latency ones, like training a machine learning algorithm or asking a human for help? So here's our problem statement. And sorry, this is a lot of text. We want a single Python script that can orchestrate our entire workflow, like I just talked about. And we have these standard building blocks in our APIs. A building block might say, go scrape this website, or go read this insurance card, or go scrape the information about this claim in the EHR. And each of our customers wants customization. And we achieve that by calling all of these APIs in different ways and different orders based on the customer's needs. But some of these API calls are very slow. So for example, performing a data entry API may take several minutes, and it's inefficient for our Python program to just block and sit there when these API calls are running. More importantly, we needed to figure out how to do retries safely. So let's say we have a 10-step automation, and we fail after step 5 of the automation. We want to be able to restart the workflow, but we don't want to just restart from the beginning, because redoing steps 1 through 5 is not only inefficient, but it's also dangerous, because sometimes we are mutating data in external systems that we don't control. For example, we're submitting an appeal if a claim was denied, or we're submitting a prior authorization. And these are things that we don't want to do twice. And we needed to make sure that we could build this in an idempotent way. So our question that kind of got us going down this road was, how can we get concurrency and retries and resuming at the point of failure while still preserving the expressive syntax of Python, and not getting into a world where we have to write our workflows in YAML or something like that, because we have so many workflows and so much customization that I think making it easy to write was one of the most important features for us. And I'll dive into the requirements a little bit more here. Yeah, first thing is that we wanted an easy syntax to write and maintain our workflows. AKASA's model is, we may end up with thousands of workflows and want to make it really easy to modify them. And we use Python internally for almost all of our software. And we want the full expressiveness of Python, including things like control flow and higher order functions. Our workflows are super dynamic and can be arbitrarily complex. So an example workflow here is like, okay, you're reading all the insurance cards, and for each insurance card, going through them one at a time, you want to scrape the image, you want to run OCR on it to get the structured insurance data. You open up a web browser and check the health insurance company, asking, hey, is this insurance still active? And as soon as you get one successful response, you break. So engineers here are probably looking at this and saying, that's a normal for loop with the break statement based on with the conditional that has a break statement inside of it. But in some workflow engines, this type of task is actually, or this type of expressiveness is actually hard to achieve, especially workflow engines that are optimized around building a DAG up front and just executing that DAG in parallel. It's actually hard to say we want to stop after we get one successful response. So that was one of the main things is we really thought Python was the right tool for us to use here. And we also wanted to get concurrency and some other nice to haves that I can talk about, like being able to prioritize certain tasks over others in case there's limited resources. So I want to take a little detour here and talk about this concept of idempotent APIs, which is kind of a key inspiration for how our workflow engine works. And just doing a quick time check here. Okay, looks like we're good on time. So this might be a review for some people, but I think it's useful to go over anyways. Idempotency is a concept from mathematics, and an idempotent operation is one that can be applied multiple times in a row without changing the result beyond the first application. So here's an example in math. Multiplying by 0 is idempotent. 5 times 0 is 0. If you keep multiplying by 0 after that, the result doesn't change. Or if you think about HTTP requests, and this is sort of assuming the rest of the state of the world is consistent, a GET request is idempotent. So if you get the same resource twice in a row, of course, assuming no one else has mutated something on the side, you're going to get the same thing back. Same with the put request. So if you are trying to update a column or a value on an object, and you run that put request multiple times in a row, you'll have the same outcome. And same with delete. So once you've deleted it once, you don't get anything extra by running the same delete multiple times. However, post is not idempotent, right? So if you submit the same post request twice in a row, you'll end up creating 2 resources. And as I mentioned, AKASA automations can mutate state in external systems, such as EHRs. And our workflows can fail partway through due to issues outside of our control. For example, we're VPNing into the customer system. If their VPN goes down, there's nothing we can do. Our workflows have to exit. And when we retry, we don't want to repeat the mutations we've already done. So that's why we need idempotent APIs to give us what's called at most once semantics, which guarantees that we're going to execute a given function at most one time. I think there's this really excellent blog post from AWS called Making Retries Safe with Idempotent APIs. And I'd encourage folks who are interested to take a deeper look at it and read it at some point. But I'll try to give the summary here, which gave us a lot to jump off of. What AWS talks about in this blog post is creating an EC2 instance, which may seem like a simple request from the client side. I'm a client and I want an EC2 instance. But internally at AWS, pulling together an EC2 instance requires several API calls. You have to make the EBS volume. You have to make the network interface. You have to make the virtual machine. And you have to tie all these things together. And each of these API calls has some failure percentage associated with it within AWS. And the question is, how do you end up with exactly one EC2 instance at the end? How do you make sure you don't end up with a random EBS volume that's floating around and not attached to an EC2 instance? And one thing they talk about is, what is the client supposed to do if it submits a request and doesn't get a response? Like maybe it submits a request and the request times out, or it submits a request and the network goes down. What's the client supposed to do? I think they agreed that reasonable behavior from the client here is to resubmit the request. And then how is the server supposed to tell if this is the same request or if this is a new request for a second EC2 instance? That's kind of the crux of the blog post. They had 2 ideas that they presented. The first idea is that on the server side, if you're AWS, you hash the parameters of the incoming request, and you use that strategy to dedupe requests that are coming in. So if you see two requests around the same time from the same origin for the same EC2 instance, with the same exact specifications, then your hash function both times is going to produce the same output. And you'll use that to infer that this is a duplicate request and say that we're not going to redo the work on the second request. Instead, we're going to assume that they didn't get the response the first time. So we'll go return the EC2 instance that we just created a minute ago. But what they bring up here is what happens if I actually want two EC2 instances and I want them at the same time, and it's me submitting both requests. Okay, how are you supposed to tell on the server side? There's really no way to tell. So they talk about this second idea, which is what they actually do in practice, which is that the client submits a unique token that's an identifier of their request. And if the client doesn't get a response, they can always retry, and they just keep submitting the same token with the request. So the purpose here being that on the server side, when you get an incoming request, you look at this client token. And if it's a client token you've already seen, that's how you know if it's the same request. If it's a new client token that you've never seen before, that's how you know that it's a different request. And they use this strategy to basically decide when to dedupe and when not to, and leave that in the client's control. And many of you may be wondering, hey, I've asked for an EC2 instance before, and I never had to submit a client token. That's because Boto3 or whatever SDK you're using is doing this for you under the hood. But the idea here is that the client can cache its token so that it can use it for retries, or you can deterministically compute the token on the client side. So idempotent APIs are very, very powerful because they lead to replayable workflows. So let me talk about that statement. At AKASA, all of our internal APIs follow the client token pattern. That means that if a client resubmits the same request with the same token within a reasonable amount of time, the response is immediately returned from the server's cache. So that work doesn't even get queued up to run again. It's cached and it's immediately returned. This is at most once semantics. So you can retry your request over and over. You're only going to actually run the function once. If a workflow fails midway through a series of API calls, then the nice part here is it doesn't actually have to remember how far it got or where it was. Instead, it can simply restart from the beginning and fire off all of the API calls again. So if the API call had already been made, then the server is going to have a record of that client token in the cache and is instantly going to return the response from the cache. Let's say we failed at step 5 in a 10-step workflow. Steps 1 through 5 return instantly when we restart from the beginning of the workflow, because all we're doing is doing a cache read. And once we get to the part that failed, step 6 in this case, we submit the request with a client token that the server has never seen before, and then the server starts doing work again. That's the idea. And this pattern leads to what we call replayable workflows. So they allow us to instantly replay all the parts that we'd already done, and then resume where the workflow left off. And we don't have to worry about work being repeated in this world. Now I want to talk about AKASA's workflow engine, which I think should be a natural transition given all of the context I've laid about idempotent APIs and replayable workflows. So one topic I want to talk about is queuing. So how this works is an engineer writes these functions or these APIs. These are the building blocks I was talking about to do things like scrape an EHR or perform data entry, or run a machine learning algorithm on a specific set of images, or call a human for help. Each of these things you can think of as API calls that follow the client token pattern. And each function is decorated with our workflow task decorator. And all of the functions are tied together in a Python script that determines the order we call them in and the control flow. And like I showed you earlier, if we want to do a for loop, and then based on the intermediate results, we want to break out of the loop, that's what you can do in this workflow Python script. And as the script is executing, rather than having the functions actually execute, what's happening is that the decorator is pushing the function calls onto a queue instead of executing them directly. So I'll stop there and just kind of repeat that. That's a really important part of our design, is that when this workflow script is executing, we're pushing these function calls onto a queue. And then the next slide, I'll talk about how those function calls actually get executed. After pushing the function onto a queue, the decorator then raises this exception we defined, which is called a pending exception, to indicate that the execution of the function is still pending. So there's nothing to see here, no results to see yet. And so the workflow exits and comes back later, and more to come on this. So the main takeaway here is that the engineer can write the code as if it's synchronous. But so for example, if they have a high latency task, such as in the middle of the night, they're asking a human for help. And even though they know that's going to take maybe a few hours to get to, they can still just write the code very simply as if it's synchronous. But the decorator actually makes it be pushed onto a queue and run asynchronously. And our Python process here, it doesn't block while it's waiting for a function to finish. Instead, it just exits, which frees up the resources it was using. So if this function was locking one of our EHR login accounts, when the workflow exits, that lock is released, and some other workflow can now go grab that lock and do some work while we're waiting for this function to execute. The second side of this, on the other side, is the workers. So we have a pool of workers constantly running. And what a worker is doing is it's in this cycle where it dequeues the task, and then it executes the function. And when the worker is done, it writes its results to the database and marks the task as done. So for our queuing backend, we use a very simple Postgres-based queue library called PQ. It's super simple, and we could use any other backend if we wanted to, but this one met all the needs we had, and Postgres was already a major part of our infrastructure. But we augment PQ in a couple of ways. The first thing we add to it is a results table to store the status, to store the status and the results of each task. So that avoids the fire and forget model that you sometimes have with message brokers, where you send something to PQ, but then, or to a queue in general, but you don't know if it ever got done or got acted upon. So this gives us a way to just query for the status and for the results of each PQ task. We also built a REST API on top of PQ that allows you to enqueue PQ tasks from anywhere on our network or from non-Python code as well, which is kind of nice. But the main summary of this slide is that workers are constantly pulling tasks off of the queue, executing them, and executing them, and then writing their results back to the database. And then we can talk about polling and notification. So, okay. So I told you that when the workflow submits a function call to the queue, it gets a pending exception and sort of immediately exits. And then the workflow retries periodically to see if this work is now done and if it's ready to continue. But what's critical about this is that there's no status endpoint. So the workflow is not saying, hey, you know, I want to hit this endpoint called /status. Can you tell me if my work is ready or not? Instead, what it does is it simply just resubmits the same request that it submitted before with the same client token. And then on the worker's end, the worker checks the cache. And if it's already seen this client token, it's not gonna run the work again. Instead, it just looks at the database and says, okay, is this task complete? If yes, I'm going to return the results of it. If no, I'm going to raise pending exception again because the task is still in progress. So this is a way that we get polling without having to deal with any boilerplate and calling a status endpoint and doing any of that. Instead, if we want to poll, we just restart the workflow from the beginning, and we get a bunch of cache reads up until the point where we left off last time. And for even lower latency than polling, something we also implemented was called notification. So what that means is that now when a task completes, it actually notifies the task that's depending on it that, like, hey, I'm done, and you're now ready to rerun if you want to. So the takeaway of this slide is that the workflow can just retry the exact same code that it was already running, and work doesn't get duplicated because of our client token pattern. I think one of my last slides on sort of the core engine, and then I'll start showing some screenshots, is around how we generate these client tokens. First thing I'll say here is one challenge we had is we needed a consistent way to serialize and deserialize the inputs and outputs of each task, right? Because we aren't executing the tasks synchronously. Instead, we're pushing them onto this queue. So we're using Pydantic to effectively act as the serialization layer between the Python code and the database, and help us consistently serialize and deserialize all of the information we need to reconstruct a task and the code we need to run. And one thing I wanted to mention is about how we generate client tokens, which I think is kind of interesting. And the framework has sort of automatically abstracted this away so that engineers don't have to think about it. So if you are a parent task in somewhere in this workflow, and you are calling your child task, what the framework does is it automatically generates the client token for the child that's a hash of the parent's client token and the arguments to the child task. So I want to be clear on that. So each task has its own client token. You're the parent, you have your own client token, and you want to call a function with some arguments. To create the client token for that function you're about to call, you hash your own client token and you hash the arguments to this function you're about to call. And what this means is that in the normal retry world, let's say we just exited due to a pending exception and we want to come back and retry. As if you're the parent, your client token is going to still be the same. And if you're going to be calling a child function, you're still going to be asking for the same arguments. So you're going to get the same hash output as before, and therefore the same client token. You're not going to redo work. But then we do have a mechanism to redo or update the work if you want to do that. So that's what I talk about in these 2 bullet points here. So if somehow the arguments to the child task change, so let's say you deploy a new version of the code and you change how you're computing arguments to the child task, or you pass in a new version identifier as an argument to the child task, then when you run this hash function, you're going to get a different client token out of it. And you end up redoing the work, which is what you want to do if you pushed a code change that like changed how you're calling the child task. Similarly, sometimes the parent client token changes. For example, sometimes you'll build a task that you say, I want this to be cached within a given calendar day, but when the clock hits midnight, I want the whole thing to rerun. And so an argument to the parent task might be some tokenized version of the date. For example, it might be the day of the week. And so if the parent client token changes, then basically all descendants of that parent also get rerun, because the parent's client token is one of the arguments as you're computing the client token of any descendant. I know this is a little complicated, so happy to take more questions on it as well. But basically the idea here is that even though we talked all about client tokens, our framework includes a decorator that automatically handles almost all of the client token generation in the manner that I mentioned above. And so engineers just write their code. They write their code as if it's synchronous, and they don't have to worry about client tokens. And the framework handles making it run asynchronously, and handles making sure that you get at most one semantics. It's worth noting that while I think this whole framework is great, it doesn't solve every problem. And one thing it requires is that you write code in a specific way. So I'll give you an example. Engineers need to be trained to not pass in like arbitrary timestamps, like datetime.now, as an argument to a function. Because if you do that, and given how I told you we're computing client tokens, which is that we're hashing several things, including the arguments to the function. If you're passing in some timestamp that you don't need as an argument to the function, then every time we run this hash function, you're going to get a different client token out of it. And you're going to keep queuing up that work to execute repeatedly, which is probably not what you want. So this requires some coding standards, but for our organization, it works for us and kind of does what we want it to do. But wanted to be clear that it's not solving every problem out there, and can be used incorrectly as well. So last couple of things that I just wanted to show some screenshots of a workflow visualizer tool we built. So AKASA is doing mission critical work for our customers, and we want to make sure that we do that safely and we have a way to audit and debug everything. So what you're seeing here is basically just the activity overview page of the workflow visualizer. So it's showing all of the different tasks that are going on, their client tokens, the queues. Basically what that means is that in our workflow engine, we support putting tasks into different queues, and then we can prioritize, set up a priority queue, basically, that says which ones to prioritize. Shows you the status, the NQDAT of each of these things, and the duration, or how long they took to execute. And yeah, this has been very helpful for us. You can then, by the way, the reason I'm not showing you a live demo is this has customer data in it, which is why I'm showing you screenshots that are blurred out a little bit. You can then click into any of these tasks to get more details. So for example, if I clicked one of the tasks from the prior page, I get here, which shows us on the left-hand side the tree of all work, starting from the ancestor, which is called do all work, and then showing all of the descendants that came from that, as well as the inputs, the outputs, and everything like that. And when we have errors, you can also click into those and see the error message, see the stack trace here, which I've obfuscated because it also had some customer data, and do some stuff like that. So that's the end of my talk. I think I'm right at the 45 minutes. So thank you so much, everybody, for listening and having me here. I'd be remiss not to mention that we're hiring all sorts of software engineers, data engineers, infrastructure, machine learning, et cetera. So you can go to akasa.com/careers or email me at sanjay@akasa.com, and I'm happy to chat.
Awesome. Thank you so much. There's a couple questions we can get to here. First one's from Bill. It was about the size of payloads. I think you were talking about the idempotency of it and being able to recall the same set of API calls in a workflow and having them you return those cached results. The question was, does this mean that your payloads have to stay fairly small?
Yeah, good question. So want to make sure I understand the question correctly. So I guess here we're talking about the arguments or the body that we're submitting in an API call, and you're asking how big can that get?
Well, I'll let
no,
Bill.
not necessarily.
Yeah, there you go.
Also, the return, which, you know, if it's large, you might get it multiple times if you make the same request multiple times.
Okay, can you repeat the question?
So I'm just curious if your engineers have to follow rules about how large a return packet, say, would be from a server request, because it's entirely possible that that return packet could be transmitted, you know, an unlimited, not unlimited, but a large number of times.
Yeah. I see. So basically, yeah, you're right. One of the costs that we're okay with is that there's going to be a lot of cache reads due to how our replay works, and that means that over and over we may be, you know, returning the same JSON responses or whatever serialized responses back to the client as it's kind of especially for, let's say, step one of a workflow. Step one is going to keep getting called every time we replay that workflow and every time we push a new function call onto the queue. So far this hasn't been an issue and hasn't caused us any scalability challenges. And our payloads do tend to be fairly small, especially because we're executing sort of small pieces of work at a time. So that's a good question, and yeah, certainly something that we are aware of is that there's going to be a lot of cache reads, and then sometimes that same response is going to be returned over and over.
So, Bill, do you actually want to answer your follow-up question about the Lambda?
Sure. So it seems to me this architecture implies that there has to be some state at the server. And I wonder, since, you know, things like AWS Lambda are all the rage, if you've thought about how you map your process onto stateless servers like Lambda.
Yeah, very good question. So we actually use Lambda to back a lot of our APIs internally. But we do have, you know, anytime we're calling a Lambda function, we're storing the inputs and outputs of that in our database. And so we basically, the idea there is that if we queue up a function call and we see that first thing we do is check the cache. And if we see that we've already ran this function and we have a response, then we don't run it again. But if we need to run the function, then that could be a Lambda function or anything else. Doesn't really matter. So some of our APIs are implemented in Lambda. And once, you know, the Lambda function runs and returns the response, then our framework is taking that and storing it back in the database. So yes, our framework does imply that there is state on the server somewhere, and we are keeping that state in our database cache. But that doesn't mean that you can't use something like Lambda. It just means you have to wrap it so that you can store the responses somewhere.
So the Lambdas then would be behind a layer of a stateful server.
Yeah,
Okay, makes sense. Thank you.
Mhm.
Awesome. So you mentioned early on in your talk that there's other workflow engines out there that implement DAGs, and that there's some shortcomings to that. I mean, could you, I guess, explain maybe a big difference between this technique, the way you're doing it, as opposed to how Airflow is doing this kind of a workflow management? Because we've written some workflows where there's human intervention in those workflows, but it sounds like you've kind of got more niceness wrapped around that.
Sure. And by the way, I will also say that I like Airflow, and I've used it, and I think it's a great tool. I think that we're solving maybe different problems or a more specific problem. So I'm also never intending to bash any technology that's out there.
I was more of a compare and contrast on what are the strengths of yours over like Airflow.
Totally. So I think what we found when we worked with Airflow is that it was too difficult to create tasks that were as dynamic as we wanted. So I'll give you an example. We don't know what steps we want to take until we start seeing the results of our intermediate work. And so I think in the workflow engine world, this is called having a data-dependent workflow engine, which means that we don't have a static DAG that we can actually express up front and say, here's our DAG, go execute this very efficiently. We actually need to start seeing the intermediate computations to decide what the rest of the call graph looks like. The other thing is that, as I mentioned with the kind of for loop example, is that ours actually is not a DAG, right? A DAG is directed acyclic graph. And sometimes we want to have cycles, but we want to be able to break out of the cycle once we've got what we need. So that's the example of for every insurance card in list of insurance cards, run optical character recognition, scrape the health insurance website to ask if this insurance is active. If yes, break out of the loop. If no, keep going. And this is something that is basically a cycle, right? If you tried to structure it as a DAG, what you do is you'd fan them all out, and you'd do the work for every insurance card, and then you'd kind of reduce it or collate it at the end and see if you got a hit or see if you got an active insurance. But we want to make valuable time. We want to make good use of our expert in the loop time, basically our operations team that might be called in to do some of this work. And so if there's 100 insurance cards and we get a hit on the second one, we don't want them to be working on the other 98. That was kind of some of the motivation. I think you could solve this type of problem in Airflow as well. But we just wanted to make it really, really easy to do these types of workflows and expressions. And that's kind of what we found, is that it felt like we were working against the tool to make it as dynamic as we wanted.
Now, I'm sure the big question everyone's interested in is, where do we see this code? Is this going to be open source at some point?
We would really like to. Yeah, we just wrapped up development and shipped our first few projects on this. And then I'm hoping that next quarter, one of our goals can be to open source it and make it available to the community for feedback and feature requests and that type of thing.
Awesome. I really look forward to that. Does anyone else have questions before I've got a couple more I can ask, but if anyone else has a question, I'd like to give them an opportunity.
I have a quick one.
Yeah, go for it, Connor.
I might have missed this earlier in the presentation, but how are the workflows typically triggered? Are they, and this, comes from my lack of familiarity with the healthcare. Is it typically scheduled or, I'd love to hear a little bit more about that.
Yeah, very good question. And I don't think you missed it. I think that's something I should probably include in this talk, is they're typically scheduled. Yeah, so there's a few different ways to do it. One is that they're scheduled based on some trigger, like a certain event happening on the customer side. Or sometimes the customer just agrees that they want it to sort of run continuously throughout the day. And so we can do things on like a cron schedule where the workflow runs every hour to make sure that it's constantly keeping up with work. So typically just scheduling it and figuring out what schedule makes the most sense for the customer.
Got it. And my follow-up question is, in the case where they're like kind of a cron sort of scheduling, and I apologize, I missed the first part of the first question, and he might have talked about that. But have you found like database? I don't know, like when I have used I've used Celery task queue library, and I found that no matter how many workers, like my database was sort of like the biggest scaling issue. And so I'm interested in whether you have run into that, and whether, but your jobs, I think, are much more like they may take a lot longer time and not interacting with the database. So I guess I'm just curious how your database sort of scaling has looked.
Super good question. So a couple of things there. First is that, so we're in healthcare and dealing with very sensitive patient data. And so one requirement that our customers have is that we actually have separate database clusters for each customer. So what that means is that we are kind of naturally sharded in that way, where we don't have one massive database that has all of the union of all of our customers' data in it. We have these sort of sharded, a large collection of medium-sized database clusters. And so that constraint, I guess, has also helped us avoid a lot of these scaling challenges on the Postgres side, because even the biggest hospital in the world is usually not going to have more data than like Postgres can handle performantly. The other thing, which was, as you alluded to, part of the first question, is that a lot of what we're doing is just these cache reads over and over and returning the same response back, which means that we can spend a lot of time indexing and optimizing those specific query paths to make those very quick. And then it's so a lot of reads and relatively little writes.
Thank you.
Follow-up question on that. Since you are leveraging or leaning on cache so heavily with an API, do you have issues like with cache invalidation or like eviction policy where things aren't in the cache when you want them and then they have to go get recalculated? I mean, how have you kind of balanced that?
Yeah, absolutely. AWS talks about this in their, I think this is a hard problem. AWS talks about this in their blog post a little bit as well, which is like, okay, I go, I ask for an EC2 instance and I pass a client token, right? And if 5 minutes later, I ask for an EC2 instance again and I pass the same client token, it's clear they should give me back the same EC2 instance. What happens if 2 months later, I ask for an EC2 instance and I pass the same client token again? That's a little weird at that point. And so they talk about this problem. We think about it as well. Generally, our idea is to expire the cache after, constantly be purging the cache after a certain number of hours, like 24 hours or 72 hours, based on what makes sense for that customer. But there are cases, especially if we start a workflow on a Friday and finish it on the next Monday or something, where 72 hours might be too short. And so, so far this hasn't become an issue, but it's kind of one of the things we're watching very closely and ready to hone in on if it becomes something we need to put more attention into. Generally the strategies there are to set some cutoff time after which doing a cache read for that same request is no longer reasonable or sensible. And at that point, past that point, if you receive the same client token again, you throw an error back to the client and say, hey, something seems off here.
Mm-hmm. Now, for caching, are you using something like Redis in that layer?
So actually, so we looked at, Celery, Redis, all of these things. So actually Postgres is our cache here. And so one of the reasons we haven't hit performance problems, as I mentioned, is that we're sort of naturally sharded out there. But because we have different database clusters for each of our customers. But we are using Postgres as our cache.
Okay, cool. And then you talked about using Pydantic to serialize data. Is that to serialize the functions into the queue as well? How do you serialize those functions into this Postgres queue? I assume you're using Postgres for the queue as well. Maybe I should back up questions.
Yes, using Postgres for both the queue and the cache. Pydantic we're using to serialize the function arguments and the outputs, but not to serialize the code. And so we have our workers that are running the code base that has access to all of the APIs. So we don't actually need to serialize the code, but we do need to serialize, whatever JSON arguments were passed in or whatever the output of each API call was. And so that's what we're using Pydantic for, is to help translate that layer.
Awesome.
So I think this ties into the question I wanted to ask, which is, what does your release process look like? Especially when you have like a change to the hash of a task. Do you have to bring everything down to do that?
Good question. So there's a couple ways we can do this, right? But we don't bring everything down, and we do sort of rolling releases. But the idea here is that one of the big challenges is this is a moving system. So if you deploy an update to the code base, how do you let the old stuff on the old version of the code keep running, but also push everything new through the new version of the code? And that's what I was talking about when we talk about generation of client tokens, which is that we don't actually have to explicitly go like invalidate the old tasks. But what happens if we push to code change is that the next time we try to run the function, if it's constructing arguments differently or calling a different child function, we're going to start getting a different call graph there, different client tokens for the descendants. And we're just going to sort of automatically start pushing things through the new version of the code. So basically, if we push a code update that changes the client token in any way, then the replay breaks and we start going down the new path that we want to go down. So this is something we definitely have to be careful about to make sure that we want the replay to break, if that makes sense. And in those cases, does that answer your question?
Yeah, it does. I guess I'm just wondering how you look at the whole thing and say, well, it's okay for those things to retry in this particular case when we're doing this release versus time.
Yeah, that makes sense. Let me see how to try to explain that. Let's see. I may not be the right person to answer that actually, but I will try to get back to you with how we're handling that.
Okay, thanks.
I got one more question unless someone else has got one, and then we'll get to door prizes. How do you orchestrate the release across the serverless components? And I assume you've got some app components that are running in containers of some kind. So it seems like you've got code across multiple different serverless technologies. What does those release processes? This is all CI driven? You got some kind of a Kubernetes that's somehow reaching out into Lambda?
Yeah, very good question. So our Lambdas are basically deployed completely separately. That's we almost treat our Lambdas as we would treat an external API as well. So the job of the workflow framework there is just to submit this API call, wait, get a response back and record it. So our Lambdas we can deploy completely separately, and we have basically a separate CI/CD pipeline for those that handles that kind of outside of the workflow engine framework. And the idea of Lambdas is, these are just API, just taking API requests and returning responses, and they don't have to care about where they're being used or how they're being used and anything like that. And then on sort of the workflow engine side, so there's a few parts we have to deploy. First, we have to deploy the workers that are kind of pulling the function calls off of the queue and executing those. And then we also have to redeploy basically the Python workflow script that has that decorator that's pushing stuff onto the queue. And so we redeploy basically all of those things together, or those two parts of it together for a given customer. And so what that means is we just bring a whole new version of it up. That's all managed with Kubernetes and swap it in. Does that answer your question?
Yeah. I think the description of them being the Lambdas being really decoupled from the rest of the release process and treated as truly microservices I like that idea of individual release processes for each of the unique parts.
Yep.
Awesome. Any other questions for Sanjay? This has been wonderful, really. Thank you so much for being with us. But if anybody's got one more question, happy to throw it in there, and then I'll do the door prize drawing. All right. If not, let's give a big round of applause, Sanjay. Thank you so much again for being here with us here at IndiePie. Super excited about it was a great talk. I really look forward to seeing the open source version of that. I think it's going to be lots of good examples sounds like a lot of good best practices for dealing with this kind of data. So that was really cool.